Imagine we learned that a huge meteorite is approaching the solar system. It's headed straight for Earth. It's actually the same size as Pluto. The unknown object must be studied. That's why, when the meteorite crosses Saturn's orbit, a huge number of small probes are sent to it. However, they did not find any minerals or useful elements at the site. At the Space Safety Center in Alaska, they install a special laser that will atomize the meteorite. And now, there is nothing left of the meteorite but video scientists working on Jupiter. And they decided to film such an event. In short, this is what life would be like if we became a Type 2 civilization. We could easily deal with any threat to our existence. We'd have an endless supply of energy at our disposal. But is everything as happy as it seems at first glance? And what could end the second type of civilization? What would we need to become a Type 2 civilization? Judging by Kardashev's scale, we need to learn how to get energy not only from sources found on Earth, but also from calcium. Link. However, it is important to note here that we are not talking about some solar power plant, but a whole system that needs to be built. About the Dyson sphere. It is named after Freeman Dyson, a professor at Princeton University who first proposed such an idea in the 60s. A Dyson sphere is a kind of huge artificial shell around a star. Its main function is to store light energy and then convert it into electricity. At the same time, some of the energy is converted into infrared radiation. The radius of such a sphere is about 1 astronomical unit. The thickness of the structure itself is about 3 meters. What are the pitfalls here? In short, things can go wrong here. First of all, the Dyson sphere needs to be built out of something, and that requires a considerable amount of resources, namely between 1.5 and 10 to the 24th power of tons of materials. Just to give you an idea of the scale, that's about the same mass as the gas giant Jupiter. Where do we get that amount of materials? Well, for one thing, we can analyze several planets with rocky surfaces, as well as all the asteroids that can be reached from our planet. However, that's not all. The materials must be very, very strong to withstand the truly destructive energy of the Sun. And the structure must be in the shape of a perfect sphere, otherwise it will be destroyed by gravitational forces. Let's imagine we've built a Dyson sphere. In this case, the difficulties will not leave us. On the contrary, for the whole mechanism to work as we need, the light must be perfectly centered. If under the influence of some external factors, the Sun moves aside, the sphere will also begin to move aside and collapse. But does that mean we can't build a large-scale structure like the Dyson sphere? We assume that people have misinterpreted Freeman Dyson's words. He proposed not a single sphere, but a group of special satellites and other special devices that would be concentrated around a star. They will accumulate the Sun's rays in themselves and then move them to Earth. Agree, this is more realistic and sounds quite complete. To do this, we need to invent and integrate technologies to wirelessly transmit power to Earth. While there should be many satellites, we still need much less material than for a solid sphere. We can create not only a Dyson sphere, but also a so-called Dyson bubble, a group of vehicles with special solar sails that fly around a star. There is also a variant of the Dyson shell, inside which it is possible to live. In fact, the options could be many. However, whatever technology we decide to create, we still face many challenges. We mentioned that we need less material for a swarm of satellites than for a solid sphere, but there are not enough of them on Earth. The only optimal option for us in this case is to look for resources outside of our planet. It's one thing to destroy a few small asteroids to do this, but it's quite another to tear apart an entire planet. That could threaten to destroy the entire solar system. Nevertheless, if we built a Dyson sphere, it wouldn't be able to deliver solar energy beyond our planet. And this would greatly reduce the likelihood of colonizing, for example, Mars in the future. It's also important to note that a Dyson sphere can only store 10% of the energy emitted by the sun per second. That portion is still huge and is 40 trillion times the daily energy consumption rate of humanity. So, this amount of energy needs to be stored somewhere. One option is to turn it into antimatter. However, we don't know how to do that at the moment, which presents us with a host of new challenges. Share, share, share. The price has been split into quarters. Don't delay, buy it now. Split. With a promotion from Alpha Bank, pick up your purchase at once for a quarter of the price and pay in equal installments with no overpayments. It seems that we were hounded literally every step of the way to create the Dyson sphere. Let's leave those points for now and imagine what happens when humanity becomes a Type 2 civilization. We will obviously spend an order of magnitude more energy than we do now, as much of it will be spent on exploration and development of solar system objects. We will have the prospect of mining the Kuiper Belt and, of course, colonizing Mars. With new materials, we will be able to create much more durable spacesuits with increased protection from solar wind and radiation. We will also be able to integrate new materials into medicine, instantly splicing bones and strengthening the skeleton, as well as changing skin and eye color. Civilization of the second type can forget about the gadgets we are used to, such as smartphones and computers. We will have a small chip with which we will actually be able to use the internet with the power of thought. This means that information will become even more accessible to us. For the second type of civilization, the approach to security will also change. Asteroids and meteorites will no longer pose a threat to us. On the contrary, we will be able to get a lot of useful resources from them. If some object does become dangerous for our planet, we will have weapons that will quickly and effectively eliminate the threat. With such weapons, it would seem that we would be omnipotent. But if another civilization came to visit us, it would likely mean a death sentence for us. If an extraterrestrial civilization approaches us, it means that it has reached the third type, which opens up the possibility of interstellar travel. A civilization can extract energy not only within its own planetary system. To a Type 3 civilization, our Type 2 civilization will seem like a bag of resources, impossible to resist. What do we do in this case? Make sure no one knows we exist. However, be prepared to be disappointed, as this is impossible due to the presence of the Dyson sphere itself. The workings of such a construct are hard to miss because of the infrared radiation it can transmit while operating. Our scientists are already studying the sources of infrared radiation to further look for signs of Type 2 civilizations. A Type 2 civilization, unable to travel between galaxies, may still find a way to escape the sad fate from a Type 3 civilization. However, we will then be saved along with the entire solar system. In the very, very distant future, we may be able to build a much larger structure than the Dyson sphere. A stellar engine. It will make the sun and all the planets move in a given direction. This is going to be a very large-scale endeavor indeed. Scientists offer many options on how to put this into practice. However, the most interesting solution to the problem was proposed by scientists Martin Rees and Seth Shustek. They suggest that representatives of the second type of civilization should transfer their consciousness into a special system of intelligent dust particles containing nanoelectronics, so we could exist in all corners of the Milky Way. It all sounds like the plot of a science fiction novel, but astronomers are now talking about it quite seriously. It seems unbelievable to us for now, but one day, perhaps it will be an everyday occurrence for humanity. The future is a delicate matter. It's in our power to bring it closer. Will the solar system become our playground? Can we become a Type 2 civilization? In 1964, Nikolai Kardashev concluded that the most accurate way to determine how advanced a civilization is to look at how much energy it consumes. The more energy a civilization consumes, that is, the more energy it can get from various sources, the more advanced it is. This is the basis of Kardashev's scale, where, for example, a civilization of the first type can use all the energy of the planet. Such a civilization has complete control over its own planetary environment, the planet's weather and resources, and the Earth's orbit. Further, a civilization of the second type would have an energy output comparable to that of the Sun. Such a civilization would use the Sun's energy as a generator, using structures such as a Dyson sphere. Finally, a Type 3 civilization would be able to harness the full power of the galaxy. This civilization would be so powerful, so advanced, that it's hard for us to even make predictions about what it would look like. Now imagine that the scale extends all the way down to Type 7. But more on that later. Now you must be wondering what humanity's place is on that scale. Carl Sagan answered this question by extending Kardashev's idea to a continuous logarithmic scale. Pi is power. Humanity's energy consumption today is about 20 terawatts. This is at 0.6, which doesn't seem too far from 1. But remember, the scale is logarithmic. Now compare that to the energy consumption of a Type 1 civilization. That's a difference of 10,000 times. Even if we allow for the trend of continued exponential growth of humanity, we will reach Type 1 status within the next century. The problem is that we seem to be on a hyper-exponential expansion path, and every year that rate gets slower and slower, moving us further and further away from Type 1 civilization. To answer the question of when we will consume the energy of the entire planet, it is necessary to choose the most probable models of humanity's development in the distant future. There are 4 of them in total. Exponential and hyper-exponential models are highlighted in red and orange color respectively. Logistic model, in green, and hyperlogistic, in blue. All of these functions do an excellent job of explaining current and near-future data. But if you go further and consider the current millennium, the data is radically different. The exponential model states that we will be able to build up our power and become a Type 1 civilization only by the year 4100, whereas the hyper-exponential model gives a forecast to the middle of the 24th century, 1,800 years earlier. The logistic functions are in the form of sloping S's and model population growth with an avalanche-like distribution, began in the 20th century. Their main feature is the limitation of the maximum level of productivity and consumption. According to logistic models, humanity will reach its peak in the coming centuries with a maximum score on the Kardashev scale around 0.65. There is no limit to perfection, and that humanity will not stop at a certain level of development, but will continue to grow to the status of a civilization of the first type. Why should it be similar? By what means will we master all the planet's sources and begin to consume 10,000 times more energy than we do today? First, let's answer the question, where do we get our energy from now? There are many types: fossil fuels, geothermal energy, nuclear fission, wind, waves, tides, and solar energy. Can we develop our technologies to improve and optimize the extraction of energy from these sources? Let's consider each of the types separately. For starters, you would think that if you have to extract all of the planet's energy, you should start from the planet's interior, from fossil fuels. But I'll disappoint you. We'll run out of it before we're even a Type 1 civilization. Sure, we won't run out of oil in 30 years, but by the year 2300, we will definitely run out of oil. Could it be fashionable to use renewable energy sources like wind and water? The fact is that air and water flows are interconnected, and by focusing on one source, production from the other will start to suffer. There is much debate about how widespread wind energy production is. Wind is generated by heating the surface of the Earth. The sun is responsible for heating the planet. The Earth's surface receives 9 out of 10 at 16 watts of energy per second from the Sun. The energy that creates wind is formed from temperature differences between regions. It is estimated that air accounts for about 2% of all energy reaching the surface from the Sun. Thus, the maximum theoretical power level achievable through wind generation is 1,800 terawatts, and that's without taking into account energy losses. What about tidal power? Tides are created by the gravitational pull of the Moon and Sun, and we have even calculated the total amount of energy transferred by cosmic bodies to our bodies of water. Altimetry and interferometry of the Moon and Sun give an estimate of 3.7 terawatts. Geothermal energy provides a power of 47 terawatts. Again, not a level where we need two competitors. Nuclear power plants utilize nuclear fission, that is, the splitting of heavy atomic elements. In the future, mankind can broadly expand the applications of nuclear fission. But even this has a limit, since nuclear power generation requires isotopes or heavy elements which are not abundant on Earth. The main favorites are uranium, Cytherium-3, i.e. isotopes of hydrogen, and lithium. The Earth contains about 35 million tons of uranium, and with an annual consumption of 100,000 tons, these reserves will be enough for the second century, but certainly not before the 24th century, when we could potentially become the first type of civilization. There are 40 trillion tons of deuterium in the oceans, which could be the salvation of future generations. But tritium, which is used along with deuterium for synthesis, is virtually non-existent. Lithium is found in seawater, but it is also not much, about 90 billion tons. Scientists predict that the collision of deuterium and tritium nuclei could cover the needs of the first type of civilization for about 10,000 years. But what about the energy of the Sun? An infinite and immeasurable fusion plant by human standards. The exchange of energy between the core and the photosphere, that is, the envelope of the star, is virtually lossless, and this potentially allows us to become a Type 1 civilization through this source alone. Can we cover the entire surface of the planet with solar panels to maximize energy? First, there is the problem of living and working space. Secondly, the efficiency of solar panels is very low. They get very hot and store only 25 to 30% of the sun's energy. The theoretical limit of solar cell efficiency is 95%. But we would rather reach Type 1 on the Kardashev scale than be able to create such a perfect energy storage device. We could launch farms of solar cells into space, cover the entire solar system with them. In general, draw energy from any image, because we know that there is an almost infinite source of energy gaping above our heads. However, there is a nuance here. Every body has a diffuse reflection characteristic, that is, how much energy the body reflects rather than absorbs. This characteristic is called albedo, that is, 30% of all energy from the sun is reflected back into space, primarily due to the oceans. Now imagine if the Earth's albedo were at 0. Then we would have enough energy to reach the level of a Type 1 civilization. But the key principle of Kardashev's assessment is not the ability to extract a certain amount of energy, but the ability to store and consume it. Obviously, there is no problem with obtaining energy. We have it in abundance. But in the future, if we don't develop consumption industries, there will be so much energy that we won't be able to not only use it, but even store it. This will cause it to dissipate as heat and cause the planet to heat up. The Earth, dotted with solar panels, will become dark and hot. The surface temperature will rise by 24 degrees Celsius. This will make most of the planet uninhabitable. And I'll tell you a fact that's not so obvious. 60% of all oxygen is released not from forests, which we call the lungs of the planet, but as a result of photodissociation of water contained in the oceans, When a photon destroys the molecule H2O and splits it into a molecule of dihydrogen, which is H2, and an atom of oxygen. Therefore, leaving the surface of all puddles of sunless light, there will be half as much oxygen left on Earth, which will also lead to the extinction of a large number of living things. Can this problem be solved? Of course! You can put all the flora and fauna, including humans, in a huge air-conditioned room. And you can make this room on another planet or in space, as shown in the cartoon Valley, where all mankind is on a huge spaceship. But it would make much more sense to explore asteroids and other planets where no one will suffer from the fact that the subsoil is being pulled out of its native places. Also, the conversation about the future of mankind inevitably leads to the question of the existence of extraterrestrial civilizations, which may be at different stages of development on the Kardashev scale. There is its alternative version, the so-called Kutz scale. It has 7 types of civilizations from 0 to 6. A civilization of type 0 is a civilization at the initial stage of cosmic expansion. We can say that we passed this stage about 30 years ago. Civilizations of the first, second, and third types repeat Kardashev's scale. Civilization of the fourth type is able to absorb the energy of the whole galactic supercollapse, a region of space several 100 million light-years in size. Then the energy consumption of the entire universe. That is the fifth type of civilization. Such a civilization can directly influence the development and evolution of the universe, as well as change the physical laws. And finally, the sixth type of civilization can affect the entire multiverse, if any. It should be noted that Helge Kaus, the creator of the scale, is a competent science fiction writer, which makes one wonder how adequate this idea is. But, as interesting as it sounds, in any case, the scale of technological development of civilization will reflect its crises and trends, and is a clear indicator of what is happening to humanity. It is believed that if the cosmos is populated by intelligent civilizations, only a few fractions of a percent of them survive to the first type. Could this be something like an elimination game? A race where you have to be the first to reach the finish line and become king of the mountain? We'll live and see. In the meantime, we continue to fantasize and do science. A stellar flare called RS Serpentor has erupted 4,500 light-years away in the constellation Serpent. This flame was so bright that it can now be seen with the naked eye. Its magnitude is about 4.8, a full 7 magnitudes brighter than normal. New stars are rare, but RS Serpens is an even more interesting case. This is because the cataclysmic variable star that flares up from time to time in front of us, and there are only 10 such stars in the Milky Way. Snake's RS has a flame periodicity of about 15 years, a white quartet in close orbit with a red giant. As they orbit each other, gas, primarily hydrogen, is ejected from the red giant by the white dwarf, which is smaller and denser. This hydrogen then collects on the surface of the white dwarf, where it is heated. Occasionally, its mass becomes so great that the pressure and temperature below cause a thermometric explosion, ejecting excess matter into space at a speed of 2,600 kilometers per second. If the white dwarf accumulates so much mass that it exceeds a critical threshold, it will become unstable and explode in a supernova. This snake may also happen with MS, but for now, the two stars continue to live in close orbits. After a quick flash over the next few weeks, serpentine MS will gradually fade and eventually disappear. The next discovery will be only in 15 years, so astronomers advise not to delay the observations. The constellation Serpent is visible to the south. It is not very bright, so it is recommended to look for a new one in the backlight, not in the city. Remember and have a good hunt. The Milky Way galaxy is a medium-sized galaxy. This galactic island may have as many as 100 billion planets. It should be noted that most of them have not yet been studied. Exploring our galaxy will probably take hundreds, if not thousands, of years from our apartment closet. And yet, each of the exoplanets confirmed by astronomers has unique features and characteristics, sometimes radically different from what you and I see. This uniqueness can manifest itself in many ways. Today we're going to tell you about two interesting exoplanets that not only orbit their closest parent star, but eventually become something more. In our solar system, the closest planet to our star is Mercury, the smallest of the terrestrial planets. It moves at a speed of 47 kilometers per second, at a distance of 58 million kilometers from the Sun. However, it is far from the record holder in terms of speed and proximity to the parent star. The name now boasts a very large Jupiter-class planet. TOI 2109b orbits a star in a star system located 855 light-years away, with a record low orbital period. It takes only 16 hours to complete its orbit. Come to think of it, you're not out of date yet. And it's New Year's Eve on planet TOI 2109b, and even though the Christmas tree is lit, there doesn't seem to be anyone there to celebrate. Because the daytime temperature is about 3,225 degrees, which is almost the temperature of small stars, so there is no such thing as light tan. TOI 2109b is about 2. At 4 million miles from its star, the gas giant is in tidal lock, and because of its close proximity to the planet star, the TOI 2109 system is an ideal laboratory. Study of planetary wave breaking by the gravitational pull of stars. Planets close to their stars that are still on the main sequence in the Hertzsprung-Russell scheme, that is, have thermometric reactions of hydrogen to helium fusion in their cores. What does this mean? Consider the following example. According to modern representatives, white swans may have companion planets. Until recently, a direct indication of this was not known. But recently, in the constellation Dragon, 80 light-years away from us, an unusual white dwarf whose companion is regularly eclipsed was discovered. It blocks most of the light that reaches the bush from the ground. According to the researchers, this companion could be a planet of the type and size of Jupiter, or, less likely, a brown dwarf. These observations were also supported by data from the Spitzer Space Infrared Telescope. The collected data allowed us to determine with complete confidence that WD 1856-534, a transiting white dwarf companion of Jupiter. On its own, this doll is nothing special. With a temperature of 4,500 degrees Celsius, it is cooler than the Sun. This means that it formed about 6 billion years ago, long before the formation of the solar system, and has had some time to cool down since then. It has about half the mass of the Sun, and its radius is 75 times smaller than that of the Sun, or 40% larger than that of Earth. Of course, it is not simple in the sense that it is an external component of the visual three-star system. Internal components. The white dwarf companion, designated WD 1856b, has a large semi-major ellipse with a length of 0.02 solar units. In other words, it is 3 million miles from its star, which is 20 times smaller than the average orbital radius of Mercury mentioned above. The radius of this body is more than 10 times that of Earth. Thus, compared to the star WD 1856-534, the object looks like a true giant. This explains the strong conservation of dwarf light that the researchers found. WD 1856b is known to have an orbital period of only 34 hours around the white quaternary. Unfortunately, the exact mass of the satellite planet is still unknown. To determine its radius, we need to know its radial velocity, which has not yet been determined. This velocity is measured by the Doppler shift of the spectral lines, which are not visible in this case. Nevertheless, we still learn something interesting when we compare the results of light conservation observations made with the giant telescope photometers on the island of La Palma with similar observations in the near-infrared region, with equipment, Spitzer telescope. Thus, the dynamics of light changes in both ranges turned out to be almost the same. After that, the exoplanet's thermal radiation flux is no more than 6% of the dwarf flux. That is, such a dark body could be a giant planet, or a very low-mass brown dwarf. Recent analysis suggests that the mass of WD 1856b should not exceed 13.8 Jupiter masses. This estimate is almost equal to, but slightly below, the theoretical low associated with the mass of brown bushes, so selection in their favor is unlikely. Based on the available information, we can confirm that we are talking about an incredibly large planet. But as a companion, WD 1856b could be 3 million miles away from the white dwarf. And how it may have escaped the star's death. The fact is that in the process of becoming a red giant, the star absorbs its planets very closely. The Sun will destroy Mercury, Venus, and possibly Earth in about 5 billion years. But how did planet WD 1856b survive? Because in its current orbit, it would have burned up long ago. The researchers suggest two plausible scenarios to consider. First, White Darvish's star was originally supposed to be a red giant before it died, blossoming with an ego the size of Earth's orbit. If a planet is at short distance, it would have been completely enveloped by the giant's outer shell, and if it had been surrounded by hot gas, it would have lost its burnt-out outer layers, but may have retained its inner chambers. Moving in a cloud of gas plasma, it was braked by friction and approached the dense core of the star, after which it threw off gas shells and became a white bush. After jettisoning, the planet was once again in gas-free space, and it entered a stable orbit around the dwarf. If the shedding of the red giant's crust is delayed, the planet will continue to accelerate and eventually collide with the star's core in a catastrophic cataclysm. Astronomers on Earth would not have expected the white owl and its companion to survive. Whether the satellite itself, a planet, or a brown dwarf, was to be completely destroyed. However, this scenario is less likely as model simulations show that it is impossible for the outer shell of the red giant to completely stabilize the satellite's orbit due to the operation of several dynamical mechanisms. Here we come to the second scenario. The same simulations show that the progeny star had multiple planets in distant orbits, and after becoming a red giant, their orbits lost their previous stability. As a result, the planet WD-1856b gradually moved into a trajectory near the dwarf, and the others, if any, were thrown into free flight through space. This restructuring can take about 1 billion years, which corresponds to the age of the white dwarf. It's like what happened, and once the planet was bigger than the star, it orbited. Yes, space is definitely an interesting place, full of interesting and even mysterious phenomena and objects. Well, for a custom James Webb telescope, there's a lot of work ahead, including learning about this amazing couple. I hope that still solves the question about the nature of the WD-1856b output. A mysterious object. However, some supernova explosions are probably not powerful enough to completely destroy nearby stars, like what happened with the LP-4365 White 4. An international team of astronomers has received new information about a mysterious object seen in 2017 dubbed the Runaway star from the hotspots. This space shuttle appears to have traveled the entire Milky Way at a speed of about 3.5 million kilometers per hour. And it's moving in the wrong direction, where most of the stars are in the center of our galaxy. Another anomaly was discovered. This object is made of a completely different material than the rest of the stars in the Milky Way. It is filled with heavy metal atoms, while other stars are dominated by light chemical elements. The incredible speed of movement suggests that the object is trying to leave the boundaries of our galaxy. Based on this fact, astronomers have proposed in a new study that such a speed could develop a celestial body that survived a violent cosmic catastrophe. It has been suspected that a supernova explosion resulting in a powerful release of energy could give the star a massive boost. This is quite possible if the object is part of a binary star system consisting of a pair of white dwarfs. The fate of such small but powerful stars is typical. Over time, one star drains so much mass and energy from its vampire-like partner that it eventually explodes. Such explosions are so powerful that they fuse the cores of old elements into completely new elements, then shoot the star in any direction. Now a new traveler with no orbit and no satellites is speeding toward the edge of our galaxy. What happens after that? Will he be able to leave the galaxy or return? We no longer recognize it. Chemical elements are the basic identifying forms of the material world. The periodic table of chemical elements is considered one of the greatest achievements of chemistry. Today, it is considered almost twice as much as it was half a year ago, when it published Dmitry Ivanovich Mendeleev's experiments on the system of elements based on atomic weights and chemical combinations. As it turns out, this sheet is the reason why our world appeared not only on Earth, but also outside. For example, the chemical composition of the Sun's surface is mostly 74% hydrogen and 24% helium. Their predominance characterizes our stellar nature. Iron, sulfur, magnesium, calcium, oxygen, etc. Elements such as are present in small amounts. Yes, almost all stars are made of gas. If the stars make sense, there is something more mysterious in the universe. For example, black holes. Of course, like the Sun, or a neutron star, most of Mendeleev's table could contain a black hole. But in what form? Black holes are a fantastic phenomenon in space. We don't know much about them. And this raises the question of whether there are elements inherent in cosmic bodies and effects in our universe that humanity does not know about. Today, we will try to understand it in short and convenient language. Physicist Richard Feynman is said to have invoked the theory of relativity to predict the end of the periodic table at element 137. His calculations showed that electrons in elements above 137 must travel faster than the speed of light, and thus violate the laws of relativity. True, recent calculations have eliminated this limit. Feynman viewed the nucleus as a single point. Let it be a ball of particles, and the elements can live up to about 173. There may be atoms beyond this limit, but only strange entities that can summon electrons from space. Relativity is not the only problem. Positively charged protons repel each other, so the more of them in the nucleus, the more stable it is. Uranium, with atomic number 92, is the last naturally occurring stable element on Earth. Each element then has a rapidly decaying nucleus, and their half-life is time. The time required for half of a material to decay can be minutes, seconds, or even fractions of a second. Atomic physics in the early 1930s seems to be a strange pattern. Nuclei in which the number of protons and neutrons is 2, 8, 20, 28, 50, 82, or 126, and were characterized by high stability or stability. This regularity was confirmed not only by physical experiments, but also by analyzing the distribution of various elements in nature. By distribution, you can judge how stable an element is. Natural reserves of elements such as tin, which has 50 protons in its nucleus, barium with 82 neutrons, and steel, which has 82 protons in its nucleus, are much larger than those of their neighbors in the periodic table. At that time, these facts did not find any explanation, and physicists began to jokingly call such a number of protons and neutrons magic. It is fortunate that this discovery was not made during the Inquisition. Then it was also noted that if both the number of protons and the number of neutrons are equal to magic numbers, the nucleus is characterized by a particularly high stability. An example of such a binary nucleus is the isotope iron 208, which has 126 neutrons and 82 protons. Current theory has succeeded in explaining the pattern of formation of magic numbers. Like the electrons of an atom, the neutron and proton shells in the nucleus are formed. The structure of atomic shells is quite different from that of electron shells, but the most stable nuclei are isotopes with neutron and proton shells filled. Thus, a superelement with a twice-magic nucleus is predicted to be element 126. A doubly magical isotope of this element must have 184 neutrons in its nucleus. This magic number is theoretically calculated to be in the region of atomic number 126, so we will be seeing isotopes for a lifetime to study their properties. But how long such isotopes will live, days, months, years, is still unpredictable. Another region of stable isotopes is expected around atomic number 114. Researchers face great difficulty in determining the properties of distant elements such as 114 or 126. Furthermore, there is no absolute certainty that there should be areas of stability. The most interesting search. If regions of stability are not found, current ideas about nuclear structure will have to be revised. If the prediction of the existence of new regions of stability of the elements is justified, it will open new perspectives for investigating the properties of transuranic elements, as well as confirm the existence of the idea and make a great contribution to nuclear physics. Structure OF is the nucleus. Of course, heavier and more unstable elements may exist elsewhere in the universe, such as dense neutron stars. But for obvious reasons, it will be difficult to study them directly, because you can quickly get into a breakdown to the table. But the good thing about modern laboratories is that they can achieve amazing results that unlock these chemical mysteries. Typically, new elements are created as follows. For example, we have a lighter atom called calcium. It accelerated and crashed into a foil of heavier atoms. If an accelerated atom moves fast enough, its nucleus, the compact nucleus of a proton and neutrons in its center, can come into contact with the nucleus of one of the heavier atoms. If this is the case, they will combine to form a heavier element. Although a sheet of foil appears solid to the human eye, it is very different at the atomic scale. The nucleus occupies only a small fraction of the space occupied by the atom as a whole. And to create a new element, the nuclei of each atom must collide and combine. It's incredibly difficult. Here's why. If you imagine an atom about 170 meters in size, the center is a tiny grape. But there is another complication. If two nuclei are headed for a collision, they must overcome a strong repulsive force that prevents them from fusing into a new element. It is called electrostatic, or Coulomb force. Only if the nuclei collide with enough energy will they overcome this force and eventually fuse together to form a new element. Let's call him Rudius. The theory so far predicts that new nuclei created in the lab will not survive long enough to form a real atom. Because less than 10 trillionth of a second, a radioactive nucleus would not have time to collect electrons around it and create a new element. But things may work differently in space. The fact is that with great gravity, constant or variable temperature, new elements of matter not only abundantly replenish the table, but can also go to a new level unknown to us. Yes, it is possible that black holes consist of a complete set, or nearly complete set, of primordial particles that decay into energy, perhaps into an indescribably fantastic conglomeration. For example, neutron stars, the precursors to black holes, are thought to have an upper mass limit of 3 solar masses. It is the maximum density of matter that is equal to the nucleus when all neutrons have all their quantum states. And these energies and forces of modern physics are known. And here the combination of these energies can create something unknown to science. What would happen if a supernova exploded near Earth? Actually, there are 3 answers, none of which are very comforting. But before we answer them, let's try to understand what a supernova birth is, and why they can harm all life, even if they are very distant. Thus, a supernova, or supernova explosion, occurs when a star rapidly increases in brightness and then collapses relatively slowly. A supernova is observed post facto, that is, after the event and its radiation reaches our keen eyes. A supernova occurs when there is a change in the center or core of a star. The change can take 2 forms, and both lead to a supernova. The first type of supernova occurs in a binary star system. A binary star is 2 stars orbiting the same point. One of the stars, white 4, steals matter from its companion star. Eventually, the white dwarf accumulates an inappropriate amount of matter, and too much matter causes the star to explode. This is how a supernova is formed. The second type of supernova occurs at the end of a star's life. When a star runs out of nuclear fuel, part of its mass falls to the core. Eventually, the core becomes so heavy that it cannot resist its own gravity. The core collapses, causing a supernova star to explode. A powerful supernova explosion is the final stage of evolution, resulting in the formation of a new astronomical body, a neutron star, or a black hole in the universe. What kind of object a supernova transforms into depends on how the next stage of evolution proceeds. If the gravitational collapse is stopped by the internal pressure, a neutron star forms. Such stars are compact, with a radius of no more than 10 kilometers, a high density of up to 1 billion tons per cubic centimeter, and 2.5 times the mass of the Sun. After a supernova explosion, 2 types of neutron stars remain: pulsars and magnetars. The former is 10 times heavier than the Sun, and the latter is 40 times heavier. Pulsars spin at high speeds on their axis, creating an energy field, and the poles emit pulses of radiation. The strength of the magnetar's magnetic field is 50 trillion times stronger than that surrounding the Earth. If the mass of the supernova exceeds the mass of the Sun by a factor of 40, there is a 100% chance that the supernova formed after the star exploded. Black holes form as a result of gravitational collapse. When a supernova has a mass of 100 times the mass of the Sun or more, this result is highly probable. Black holes attract an incredibly large amount of particles every second, quantities comparable to millions of Earth masses. Excess energy is emitted back into space as radiation. Such is the future of our nearest stars. Yes, it's Betelgeuse, which is 20 times more massive than our Sun. It is now in the red giant stage, albeit a long-term dead stage. Betelgeuse is one of the brightest stars in the sky. The red dot in the constellation Orion continues to amaze with its mysterious behavior. At the end of 2020, it faded, but now it is back and has become 50% brighter in a few weeks. This is what led to rumors that Betelgeuse would explode. It's not hundreds of years, it's decades or even years. Eventually, when the star runs out of fuel, it will collapse due to gravity and go supernova. What if Betelgeuse explodes now? Should we pack our bags and gear and grab a bloody guinea pig for the bunker? Yes. Sometimes people start doing things when it's too late and after the last star has left the station. And it is better to prepare everything in advance. So if it's ethyl juice, we shouldn't expect much danger. Yes, the spectacle would be spectacular, but the earth would not be shaken by the shock wave. The towers of heaven would not fall like staves. The sea would not rise like walls, and the inhabitants would not be kindled by fire. The last day of the apocalypse. I'm sorry, Thanos. So what do we see? According to calculations, it should be the second supernova explosion. This means that Betelgeuse, to an observer in its own system, will briefly be 500 million times brighter than our Sun. Yes, indeed, it is blindingly bright. But of course, we don't roll Betelgeuse. How bright will Betelgeuse be for us? Given the distance from Earth to the giant, calculations show that Betelgeuse will be about half as bright as the Moon. Betelgeuse will be visible both during the day and at night. But it will not be like the second Sun. During the day, Betelgeuse will appear as a large, bright spot. Larger than an ordinary star, but smaller than the Sun. At night, Betelgeuse will appear as a large, bright cloud, comparable in brightness to the Moon. Over the coming months, Betelgeuse will begin to fade, but will remain visible during the day for 6 months, or up to a year. For another 2 years, it can be observed with the naked eye in the night sky. Only then will it disappear. Unfortunately, not a single dome is visible around an exploding supernova at a time. That's a long time, so we'll have to wait a few more years before we see a spectacular dome around a once-dead star. Astronomers with their powerful telescopes will soon be able to see the star's crust. Fact: the big boss in Betelgeuse is 642 light-years from Earth, so its supernova maximum will shower our planet with massless particles called neutrinos. Fortunately, they cannot harm us. We travel into space to make discoveries and look beyond reality itself. What if the cosmos is invisible in all its glory? Could it be that our universe is an illusion, a complex facade covered by the complex laws of physics? Our quest leads us into a labyrinth of time, moving endlessly through the universe. Time stretches, compresses, and binds all aspects of existence. It acts as an invisible link, connecting the past, the present, and the uncertain future, forming the foundation of our reality. As our journey reaches its climax, we will encounter 2 formidable pillars of understanding: the speed of light and the mysterious force of gravity. The speed of light, the boundary that separates the possible from the impossible, and gravity, the invisible force that represents the interaction between all matter, bending the fabric of space and time. Through them, we will try to decipher the cosmic code that governs the universe. Fasten your seatbelts for an unknown space journey, where we challenge our understanding of the universe based on the principles of time, light, and gravity. Everything around us, even ourselves, is part of our universe. We are used to thinking of it as something ephemeral, but what is the universe? Today, we're going to challenge what you know about the universe. What if everything we see and feel is an illusion? Hold on, because we're about to delve into the mysteries of the universe. First, let's look at what we know about the universe. For scientists, the paradox of how our universe was formed is still a mystery. As we know, 13.8 billion years ago, according to the Big Bang Theory, the universe was formed from a singularity where all the fundamental forces converged. On the other hand, according to the Hawking-Hartle theory, the universe did not originate from a single point. It existed as pure space without time. with the Big Bang coming later. Despite the diversity of current ideas about the origin of the universe, cosmic inflation began at some point. Protons and neutrons formed in microseconds, forming basic building blocks like hydrogen and helium. Then, after cooling, 360,000 years later, light, and millions of years later, stars and galaxies. As a result of the expansion caused by the Big Bang, we can see other galaxies moving at high speeds. And so, 1 billion years after the Big Bang, the universe as we see it came into existence. But what do we mean when we talk about the observable universe? The part of the universe that we can see may not be very large. It's actually about 93 billion light-years. What each of us sees is the matter and energy that fills space. Surprisingly, the fraction of ordinary matter that makes up stars and planets is tiny compared to the hypothetical dark matter we have yet to detect. However, the most interesting thing we know about the universe is life. According to the principles of physicist Brandon Carter, we exist as observers, and the universe conforms to our existence. And the universe must be like observers. That is, the universe can be such that our existence is possible. This leads to the fundamental question: does the universe exist apart from us? Let's turn to quantum theory. Physicist John Wheeler, colleague of Albert Einstein, modern observations suggest that they can influence the behavior of photons. A famous experiment with photons directed at two pieces, and a screen shows that observers with detectors can influence the behavior of photons. Thus, if there are observers, the photons act like particles and pass through one of the two slits. However, without observers, the photons behave like waves and pass through two slits at once. Wheeler decided to take the experiment to the cosmic plane, pointing the photon gun at the quasar and moving the slits to two nearby galaxies. Thus, the photon may have started billions of years ago, before life and the development of photon detectors, forced to go to those detectors. That is, the motion of light always depends on the observer. Does this mean that the universe cannot exist without humans? Not really. It is true that humans are capable of receiving information, analyzing it, and reproducing it for others. But they are not the only watchers, even if they are perfect. Following Wheeler's model, high-energy particles, which can exist in different states, can interact with rocks on Earth. Thus, the stones will leave a trail of particles, which means that new information has been exchanged. Therefore, according to this hypothesis, the universe does not need consciousness. Another experiment in quantum mechanics confirms this. 3 scientists who recently shared the Nobel Prize, John Clauser, Alain Aspect, and Anton Zeilinger, were able to prove that the universe is not local. This, of course, does not mean that the universe as we know it does not exist. Physics distinguishes between the principles of reality and locality. Reality means that an object exists and does not change its properties even if no one observes it. A red apple will remain with or without measurements. Area, in turn, is explained by the fact that objects can be affected only when they are related to each other. And these distant bodies cannot interact with each other, for example, at the speed of light. If you send a light signal to a friend 10 light-years away, you won't get a response after turning on the flashlight. This leads to the principle of local realism or the principle of hidden variables, according to which objects with certain characteristics exist at some intangible level and are independent of observations. In other words, we live in an objective reality with a certain set of factors, independent of our consciousness. But physicist John Stuart Bell disagreed. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper under the acronym EPR, in which the theorists attempted to prove the absurdity of quantum physics. They questioned the possibility of quantum communication. If two particles are bound, They are conserved even if they are in different parts of the universe. For example, if a particle rotates clockwise, other particles associated with it rotate counterclockwise. So, if one piece is on Earth and the other piece is 1,000 light-years away, then, knowing the direction or rotation of one of them, one can immediately know in which direction the other is rotating. This contradicts GR because nothing can travel faster than light. So, 30 years after EPR was published, Bell conducted a thought experiment. He continued with the EPR idea, but refined it a bit. He envisioned two observers, Alice and Bob, in different parts of the solar system and with particle detectors, but with two different settings, A, B, B, for more precise observations. Thus, if the local theory of reality were true, one particle would have no way of knowing what parameters another has. Results are always random. If quantum theory is correct, then the particles would be perfectly correlated. 3 Nobel laureates, Clauser, Aspect, and Zellinger, were able to replicate the experiment in reality. By counting the number of times Bob and Alice agreed with each other about the state of the particles, they confirmed Bell's theorem, proving that the universe is not locally real, meaning that everything in the universe needs an observer. That's why we can breathe. The universe exists as we think it does. However, what if I told you that this might not be the case and that our brains are deceiving us? From our perspective, according to Einstein's GR, the universe is a continuum of space-time with 3 dimensions and 1 temporal dimension. All massive objects in our universe, including our Earth, can cause gravity to dissipate time. Yes, we monitor all of this. What could be cheating? Perhaps our 4-dimensional universe is a holographic projection. It sounds fantastic, but this theory is being seriously considered by scientists. Everyone has probably seen a hologram, a deep 3-dimensional image created on a flat surface using light. The light produced by the holograms contains a large amount of encoded information. For example, texture or relative distance. Thus, from all angles, the image will appear 3-dimensional. Theoretical physicist Juan Maldacena suggests that our universe might be like this. Everything you see in 3 dimensions is in 2 dimensions. Black holes helped develop this idea. Black holes can increase their mass at the expense of other objects falling onto them. But these objects do not disappear. They remain in the black hole. But black holes can decay. Renowned physicist Stephen Hawking discovered that black holes evaporate and then disappear completely. What happens to data that falls into a black hole? Will it be gone forever? This goes against the basic laws of physics because matter cannot disappear. They change to another state according to the principle of conservation of mass. However, the idea of the holographic nature of the universe can solve this paradox. The holographic theory is explained through the hypothetical doubling of 2 other mathematically equivalent theories, the ADS-CFT correspondence. Anti-de Sitter space, ADS, a space closely related to negative space and constant theory, has a curved parabolic shape in more dimensions than required by line theory. This space is often defined as 5 dimensions, but it can have up to 10 dimensions. ADS also has limitations, unlike the popular model of the universe. Modern cosmology suggests a flat universe model, similar to a simple universe, where 2 lines or 2 light waves will always be parallel. If the universe is truly perfect, it may not have boundaries. But it's possible that our universe is so warped in unimaginable disintegration that satellites can't see it. Therefore, the UDS can be thought of as a 3-dimensional ball with a finite surface, but it is very flat. This theoretical limit is crucial for the second theory in this theory, conformal field theory. CFT describes the behavior of particles and fields in flat space and is one-dimensional compared to ADS and has no particular gravity. So there is a dualism that allows us to look at the system from two sides. Internally, what is in ADS can be translated to CFT and vice versa. So their duality is like a borderline hologram, encoding everything inside. Thus, according to ADS-CFT, information entering a black hole does not disappear without a trace. Information can be encoded in the two-dimensional event horizon of a black hole, beyond which the gravitational disturbance is so strong that even photons cannot escape. Thus, the data is not lost, only moved up. This duality theory does a good job of explaining these and other modern mysteries of the universe, but it has several problems. For example, the ADS-CFT correspondence works in a negative spatial constant universe model. However, according to current observations, our universe has a positive constant value and is still expanding. So, we probably don't live in a finite universe. For example, in 1929, astronomer Edwin Hubble concluded that the universe was continuing to expand and that this process could continue forever. Therefore, since our observations are limited, the question of the infinity of the universe remains open. This point is crucial to the whole theory. So now the idea of ADS-CFT has mathematical value. But if we can find answers to all the findings of the theory, we can prove that the universe is a hologram. The question of what our universe is worries not only physicists, but also philosophers. In 2003, philosopher Nick Bostrom suggested that some scientists, such as Elon Musk, think it's somewhat possible. What if we are living in a simulation? In his paper, Bostrom argues that one claim about simulation capability must be true. First, humans will die before they reach a technological level that would allow them to create the most complex simulations. Second, it is highly unlikely that an advanced civilization would be interested in imitating its history. 3 advanced civilizations are creating simulations, and we live in one of them. So, if the third idea is true, we could live in a completely simulated world like computer games. Of course, this hypothesis cannot be tested empirically, but we may have some evidence to support the simulation hypothesis. About the speed of light. According to Einstein's theory, we know very well that the speed of light is limited to 186,000 miles per hour. Therefore, all the light we see from the stars takes a long time to reach us. A simulated device cannot have unlimited computing power. There must be some limits, and it's these limiting artifacts that we can observe at the limit of the speed of light. So, if this hypothetical computer processor running the simulation could perform 1 operation per second, it will have a warranty of 186,000 miles. In particular, the simulation can also explain the principles of quantum mechanics. As with subatomic particles, we define their state by looking at them. Thus, based on the simulation hypothesis, we see only the indicated part of the universe graph, and the rest of the graphs remain empty. And yet, despite the interesting explanation, by limiting the speed of light, a simulated universe is considered a speculative hypothesis because it cannot be proven or disproved. Maybe someday, if this hypothetical computer matrix starts to fail, we'll reconsider this idea. So, the universe is still a great mystery to us. We cannot believe that everything we see is not an illusion. As we have said, we are aliens to the universe, but what if we should never live? The Earth, the Sun, and our galaxy were never meant to be. CERN scientists believe that symmetric matter and antimatter must have been created after the Big Bang. So, if this scenario were to happen, all the particles had to come together to destroy the whole. However, something has created an imbalance between the two substances, and it is not yet known what it is. So we can say we are happy because we are here now, and we would be able to observe the universe and discover all its secrets. Do you think that one of the most fundamental aspects of our lives is nothing more than a complex illusion? Time, the force that governs our existence and seems to dictate the rhythm of our lives, is not what it seems. For example, time seems to slow down for objects traveling near the speed of light, and it flows at different speeds depending on the force and gravity around us. Have you ever considered that time may be a figment of our imagination, a construct our brains come up with to make sense of the world? In search of the truth behind this mysterious concept, you will have to step into the unknown and question everything you know about time. Time, in its simplest form, is a tool we use to measure change and organize the complex events that make up our lives. Our ancestors needed a way to keep track of natural cycles, like day and night, or the changing of the seasons. It was important in coordinating activities such as farming, navigation, and religious rituals. Early methods of telling time were based on natural phenomena, such as sunrise and sunset, the phases of the moon, and the positions of the stars. As human society has become more complex, so have our ways of measuring time. To divide the day into smaller and more manageable parts, we developed instruments such as sundials, water clocks, and finally, mechanical clocks. Calendars are designed to track the passage of long periods of time, such as months and years. Different cultures have developed their own unique calendars and timekeeping systems, reflecting the diversity of people's understanding and interpretation of time. Although timekeeping systems help us manage our daily activities and long-term planning, the perception of time remains a deeply personal and subjective experience. Our brain processes and interprets time differently, depending on factors such as age, emotional state, and cultural background. This suggests that time is not a fixed universal phenomenon, but a flexible construct shaped by our experiences and needs. Despite the presence of time in our lives, it remains a somewhat illusory concept. This begs the question, is time an objective reality, or is it a construct created to bring order to our chaos? So, let's look a little deeper into the history. The traditional understanding of time as an independent, constant entity was challenged by Albert Einstein's groundbreaking work in the early 20th century. Einstein's theory of relativity introduced the concept of time as a measurement, forever changing the way we think about this mysterious phenomenon. Einstein's theory of relativity arose from the nature of light and the concept of absolute space and time that was central to classical physics. He argued that the laws of physics must be the same for all observers, regardless of their relative motion. This revolutionary idea led to the development of two related theories: special relativity and general relativity. In his theory of special relativity, Einstein showed that space and time are not separate entities, but are bound together in a single continent called space-time. In this four-dimensional frame, time is transformed into a fourth dimension, and events are represented as points in space-time. This concept overturned the traditional view of time as an independent variable, showing that it is an integral part of the structure of the universe. Einstein's theories also showed that time is relative and depends on the reference of the observer. According to the theory of special relativity, two events that appear to one observer at the same time may appear to move relative to the first to a second observer at different times. This phenomenon, also known as relative relativity, makes it difficult for us to perceive time as an absolute and constant unit. General relativity extended the ideas of special relativity and brought gravity into the picture. According to this theory, large objects such as planets and stars cause periodic distortions, and this vein is captured by the force of motion in it. The presence of a large object can also affect the passage of time, resulting in a phenomenon known as gravitational time dilation. According to the theory of special relativity, time dilation occurs when two objects are moving at relatively high speeds relative to each other. If an object is moving faster, time passes more slowly compared to a stationary observer. This effect becomes apparent when approaching the speed of light. This phenomenon is best illustrated by the famous twin paradox. In this case, one twin travels close to the speed of light, while the other twin remains on Earth. Upon return, the traveling twin will be younger than the earthly twin due to the time difference. In general relativity, time dilation is also caused by gravity. Time moves more slowly in stronger gravitational fields, such as near large celestial bodies such as planets or stars. This effect was tested experimentally using atomic clocks located at different altitudes. Clocks closer to the Earth's surface run slower than clocks at higher altitudes where gravity is stronger and gravity is weaker. Time dilation, although seemingly illogical, has been experimentally verified and has practical applications. The best example is the Global Positioning System, or GPS. Earth-orbiting GPS satellites experience time dilation due to acceleration and gravity, which must maintain accurate time and location. Furthermore, gas pedal experiments for high-velocity particles have confirmed that particles traveling at the speed of light experience significant time dilation, as predicted by the theory of special relativity. Before Einstein's theory of relativity, time was considered the unchanging and universal background for all events in the universe. Isaac Newton, for example, believed in the concept of absolute time, which is uniform and flows independently of the events it measures. However, discoveries related to time expansion. The theories of special and general relativity refute this notion with the relative nature of time, and prove that time is not a constant but a variable quantity depending on the motion of the observer and the surrounding gravitational field. The traditional view of time as an absolute entity also implies a strict adherence to casuistry, where cause always precedes effect. However, the relative nature of time in relativity theory suggests that the order of events can depend on the reference of the observer, which can lead to cases where cause and effect appear to be reversed or simultaneous. This complicates our intuitive understanding of randomness and forces us to rethink our ideas about the way things work in the universe. The concept of the arrow of time, the idea that time flows in one direction, from the past to the future, based on our understanding of the world, has also been questioned. However, relativity's relativistic nature of time and random reversals force us to reconsider whether the arrow of time is a fundamental aspect of the universe or a construct of human perception. As the traditional view of time as an absolute entity was undermined by the discoveries of relativity theory, some scientists and philosophers suggested that time might be an emergent property rather than a fundamental aspect of the universe. From this point of view, time arises from the connection and interaction between objects and events, rather than being independent of them. Leaving aside the problems of Einstein's theory of relativity, we move into the more confusing world of quantum mechanics. In this realm, the nature of time becomes confusing and ambiguous, as the rules governing the quantum world defy our everyday understanding. Quantum mechanics is a branch of physics that studies the behavior of particles at the atomic and subatomic level. It is governed by a set of probability rules that differ from those of classical physics. In the quantum world, particles can exist in multiple states at once, a phenomenon known as superposition, and their properties can only be determined by measurement or observation. The concept of time in quantum mechanics is very different from the concept of time in classical physics. While classical physics describes time as a continuous and absolute unit, quantum mechanics treats it as a discrete numerical parameter. This time leads to situations that lose their traditional meaning and play an abstract role. For example, consider the following everyday scenario. You watch wild animals and see how they behave differently when they know they are being watched. As you get closer to them, their behavior changes, and it becomes difficult to understand their natural state. This example illustrates the observer effect in quantum mechanics, also known as Heisenberg's uncertainty principle. In the context of quantum mechanics, the observer effect refers to the idea that active measurements or observations can perturb the state of a quantum object, such as an electron. Just as your attempt to observe wild animals affects their behavior, observing or measuring a quantum object can affect its position or momentum. Heisenberg's uncertainty principle states that the position and velocity of a quantum object can be known simultaneously with absolute precision. The more accurately we measure one property, the more accurately we can know the other. In the quantum world, the act of observation or measurement can collapse the wave function of a particle and move it from a superposition of multiple states to a specific state. This process is inherently problematic, and the outcome cannot be predicted with certainty. Considering the phenomena of quantum superposition and the observer effect, it becomes clear that our traditional understanding of time as a linear progression may not be correct at the quantum level. Instead, the quantum world offers a more fluid, interconnected vision, where the boundaries between past, present, and future are not as rigid as we think. As we have seen, our understanding of time is closely related to our understanding of space. This complex relationship has given rise to many theories that attempt to explain the nature of space. The periodic fading of stars in the Crab Nebula is caused primarily by the presence of a neutron star at its center, known as the Crab Pulsar. This pulsar is a strongly magnetized rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. As the pulsar rotates, these rays spread through space like a lighthouse beam, creating the phenomenon of periodic dimming or pulsation when viewed from Earth. As it rotates, the pulsar produces intense bursts of radiation over a range of wavelengths, including radio, optical, and X-rays. When the beam of radiation is directed toward Earth, the star appears brighter. As the beam spins sideways, the star dims. This periodicity is incredibly precise. The Crab pulsar makes one revolution about every 33 milliseconds. The regularity of this pulsating effect is one of the most interesting characteristics of pulsars, providing important information about the rotation and magnetic field of the stellar remnant. The environment surrounding the pulsar is also significant. The Crab Nebula itself is the result of a supernova explosion that produced a pulsar in 905 AD. The expanding supernova debris interacts with the pulsar's magnetic field, creating a complex structure of shocks and radiation in different wavelength ranges. This interaction generates additional radiation that contributes to the observed brightness changes associated with periodic dimming. Studying the periodic dimming of the Crab Nebula, which is primarily due to pulsar activity, not only deepens our understanding of the life cycle of stars, but also provides insight into the physics of neutron stars and the extreme conditions that exist in their neighborhoods. Pulsars like the Crab Nebula provide a natural laboratory for studying fundamental questions in astrophysics, contributing to our understanding of the behavior of the universe and the life cycles of celestial bodies. The phenomenon of some stars appearing older than the universe itself is a fascinating mystery in astrophysics, arising from various factors related to the formation and measurement of stars. The age of the observable universe is estimated to be about 13.8 billion years old, based on cosmic microwave background radiation and other cosmological data. When astronomers observe certain stars that appear to be older than this time interval, this provides a deeper look at the intricacies of stellar evolution and the difficulties in age estimation. One of the main reasons for these apparent age discrepancies has to do with the methods used to determine the age of a star. Astronomers often estimate stellar age based on a star's position on the Hertzsprung-Russell diagram, where stars are arranged according to their brightness and temperature. However, this method can lead to uncertainties, especially for stars in later stages of evolution. If the star is in a part of the diagram that suggests a much older age, this may not accurately reflect its true age if the underlying assumptions about evolutionary processes are flawed or incomplete. Another factor contributing to this paradox is the nature of the star's composition. Stars with high concentrations of heavy elements, known in astronomy as metals, usually form after previous generations of stars have evolved and died, enriching the interstellar medium. Therefore, a star with low metallicity may indicate that it was born from primordial materials, suggesting that it has existed since the early universe. Nevertheless, stars with lower metallicity may appear older than they actually are because of the complexities of stellar dynamics and life cycles. In addition, some stars are part of globular clusters, which are dense clusters of ancient stars. The age of these clusters is difficult to determine precisely. The oldest globular clusters are estimated to be nearly 14 billion years old based on stellar models, making them seemingly bumping up against the upper limit of the age of the universe. Such a coincidence calls into question the very models we use to estimate stellar ages and star formation histories in the cosmos. In conclusion, the apparent older age of some stars challenges our understanding of stellar evolution and highlights the need for improved modeling techniques. As researchers continue to study these celestial objects with modern telescopes and improved techniques, we can further understand the tangled history of our universe and the stars that inhabit it. Ultra-luminous X-ray sources, commonly referred to as ULXs, are unusual astrophysical phenomena found in various galaxies beyond our planet. They are characterized by incredibly high X-ray luminosity, 1,000,000 times the luminosity of the Sun. ULXs are of great interest to astronomers because they are some of the most intense X-rays observed in the universe and produce emission that often exceeds that generated by typical stellar sources. The exact nature of ULXs remains the subject of active research, but they are generally thought to be associated with binary systems involving a compact object, such as a black hole or neutron star, that accretes matter from a companion star. In particular, many ULX are thought to host black holes with masses ranging from a few to a few tens of solar masses, distinguishing them from the stellar mass black holes commonly found in our galaxy. The accretion process occurs when the matter of a companion star flows into a black hole, generating enormous amounts of energy as the falling material heats up and emits X-rays. Another intriguing possibility is that some ULX may be associated with intermediate mass black holes, which are a missing class of black holes that have masses between 100 and 1,000 solar masses. The detection of intermediate mass black holes in ULXs can shed light on the formation of supermassive black holes at the centers of galaxies, which can have masses millions or even billions of times that of the Sun. In addition, ULX can exhibit brightness variability, indicating a change in accretion rate. Sudden outbursts and fluctuations can provide additional insight into the dynamics between the accreting matter and the compact object. This variability often makes ULX a rich field for studying the fundamental physics of black holes, accretion flows, and the environments in which they exist. The study of superluminous X-ray sources continues to advance with advances in observational technology and observing campaigns in both the optical and X-ray wavelength ranges. As we learn more about these mysterious objects, they open a unique window into the extreme astrophysical processes and interactions between stars and their compact remnants, enriching our understanding of the cosmic landscape. Each discovery adds another layer to the tangled tapestry of the universe and spurs the quest to comprehend the fundamental nature of matter and energy in extreme conditions. The phenomenon of some galaxies having almost no star formation despite an abundance of gas is a fascinating area of research in astrophysics. At first glance, this seems counterintuitive. The presence of large amounts of gas, which is the primary fuel for star formation, should lead to active starbirth. However, various factors can inhibit this process, leading to a condition known as star formation fading. One important reason for this attenuation has to do with the dynamics within the galaxy itself. In some cases, the gas in such galaxies may not be dense or cold enough to collapse into stars. Factors such as turbulence or heating from existing stars can prevent the gas from cooling and condensing, creating a barrier to star formation. For example, in some massive elliptical galaxies, the presence of supermassive black holes at their centers can drive powerful winds or jets that heat the interstellar medium, effectively slowing or stopping the cooling processes necessary for star formation. Moreover, galaxy mergers and interactions can greatly affect the rate of star formation. When galaxies collide, they can direct gas toward their centers, causing bursts of activity. But in other cases, these interactions can cause the gas to be expelled from the galaxy or redistributed in a way that prevents star formation. Gravitational forces can carry the gas away or create conditions that stabilize the gas against collapse into stars. Another factor may be the role of dark matter and the overall gravitational potential of the galaxy. For galaxies in which there is no active star formation, the binding energy of the dark matter halo may not provide the conditions necessary to effectively trap gas. Reduced gas volume resulting from interactions with the environment or from the higher gravitational potential in a galaxy cluster can also remove gas that would otherwise be available for star formation. In addition, the role of the cosmic web cannot be ignored. The large-scale structure of the universe affects the flow and distribution of gas. In some regions, the influx of gas from the intergalactic medium may be suppressed due to the large-scale environment, further limiting the amount of gas available for star formation. Understanding why some galaxies can retain significant amounts of gas without turning it into stars provides critical insights into the evolution of galaxies. By delving deeper into this topic using advanced observational and modeling techniques, researchers aim to unravel the complex interplay of gravitational, hydrodynamic, and chemical processes that have shaped the life of galaxies throughout cosmic history. Each new finding deepens our understanding of galaxy formation and evolution, revealing the complex nature of the universe in which we live. The ripples observed in the Milky Way disk are a remarkable phenomenon that allows us to understand the dynamics of our galaxy. These pulsations are primarily caused by the gravitational interaction of stars within the disk, as well as the influence of nearby structures. One important contributing factor is the passage of spiral arms. As stars and gas clouds move through these arms, they experience a gravitational pull that creates perturbations that result in wave-like shapes in the distribution of stars and gas. In addition, interactions with companion galaxies play a crucial role in creating these ripples. The Milky Way is not an isolated entity. Several small galaxies, such as the Large and Small Magellanic Clouds, orbit nearby. The gravitational attraction of neighboring galaxies can cause tidal forces that affect the distribution of stars in the Milky Way disk. Over astronomical time, these interactions can accumulate and create the observed waves or ripples in the galaxy structure. Another interesting aspect is the potential involvement of dark matter. Although we cannot see dark matter, it is believed to make up a significant portion of the galaxy's mass. Its gravitational influence may also contribute to the movement of stars, resulting in these rippling patterns. This concept allows scientists to study the influence of dark matter indirectly, through the behavior of visible stars. Researchers continue to analyze data from telescopes and other instruments and reveal the complexity of the Milky Way's structure. Understanding these ripples not only helps us understand our own galaxy, but also sheds light on the interactions occurring in other galaxies throughout the universe. Each ripple tells a story of cosmic motion and the gravitational dance between celestial bodies. The intricate and symmetrical shapes of some planetary nebulae result from a complex interplay of processes late in a star's life. When a medium-sized star like our Sun exhausts its nuclear fuel, it undergoes a series of transformations. When the core contracts and heats up, the outer layers of the star are ejected into space, forming a glowing shell of gas and dust known as the planetary nebula. The symmetry often observed in these nebulae can be explained by the dynamics of the ejection process. One of the main factors influencing the shape is the role of magnetic fields. When a star sheds its outer layers, magnetic fields can create organized structures within the ejected material. These fields help direct the flow of gas, resulting in more uniform, complex shapes rather than random distributions. In many cases, these magnetic fields also interact with the stellar wind, a stream of charged particles ejected from the star, reinforcing this ordered structure. In addition, binary star systems contribute significantly to the formation of symmetric shapes. If a star exists in a binary system, interactions between two stars can lead to mass exchange and the formation of ejected material. A single star can shed its outer layers while a companion gravity attracts and directs this material, creating a more structured and recognizable shape. This gravitational interaction can lead to the formation of jets and lobes that produce the unique and often beautiful shapes we observe. The combination of these processes creates the breathtaking patterns observed in planetary nebulae, which can range from circular and spherical to more complex shapes, including intricate knots and filaments. Studying these structures not only deepens our understanding of stellar evolution, but also provides clues about the physical conditions late in the life of a star. Each planetary nebula is a snapshot of cosmic processes, demonstrating nature's mastery of the universe. The interstellar object known as Oumuamua has intrigued scientists since its discovery in 2017, providing a unique opportunity to study a visitor from outside our solar system. Oumuamua is believed to have a rocky or metallic composition, and its unusual shape is elongated and cigar-shaped, which is very different from typical asteroids or comets found in our solar system. The name Oumuamua comes from the Hawaiian language and means scout or messenger, which is quite reflective of its status as the first detected interstellar object to pass through our planetary neighborhood. Scientists hypothesize that Oumuamua originated from a star system beyond our planet, as a result of an ejection from its home galaxy. This ejection could have been caused by gravitational interactions with other stars, which could have caused it to be flung away at high speed. Freed from its original star system, Oumuamua traveled the vastness of space for millions of years, eventually making its way to the inner solar system, where we discovered it. Another intriguing aspect of Oumuamua's journey is its trajectory. As it traveled through the solar system, the object exhibited unusual acceleration, which some scientists initially attributed to outgassing, a common phenomenon observed in comets. However, the lack of a visible comet-like tail led researchers to consider alternative explanations, including the possibility that it was a fragment of a larger body, or perhaps playing some role in the complex dance of interstellar dynamics. Ultimately, Oumuamua serves as both a scientific mystery and a reminder of the dynamic nature of the cosmos. Its presence raises fundamental questions about the distribution of interstellar objects and the processes that govern their movement through space. Through continued research and observations, scientists hope to learn more about the origin and properties of such guests, leading to a deeper understanding of the universe beyond our solar system. The presence in some star clusters of several populations of stars with different compositions provides a glimpse into the complex history of these celestial formations. In particular, the phenomenon is most prominent in globular clusters, ancient groups of stars orbiting galaxies. The different populations can be attributed to the environment in which the clusters formed and the subsequent evolutionary processes through which they passed. One of the main reasons for the multiplicity of populations is the initial conditions of cluster formation. Many star clusters formed in dense regions of gas and dust, where the first generation of stars created heavy elements through nuclear fusion. When these stars reached the end of their life cycle, they enriched the surrounding matter with heavier elements, a process called metallicity. The enriched gas subsequently became the raw material for the next generation of stars, giving rise to a second population with a different composition, often exhibiting higher metallicity than the first. In addition, the diversity of stellar populations can be facilitated by interactions between stars within a cluster. As stars evolve, some of them may eject material that can be accreted by younger stars, further changing their chemical composition. It is also hypothesized that in some clusters, periods of star formation extended over millions of years. These intervals allowed different compositions to form as the stellar environment evolved. Moreover, in some cases, the detection of multiple populations challenges previous ideas about how star clusters evolve. The idea that globular clusters may have formed from the merger of smaller clusters suggests that what we see today is a mixture of different star formation sharing space in the gravitational capture of the cluster. This complex interplay of formation history and stellar evolution makes the study of star clusters particularly fascinating because they reveal the processes that shape the universe on vast scales. Each cluster contains a wealth of information about the life cycle of stars and the chemical evolution of galaxies. The periodic brightening of the blazar OJ 287 is a surprising phenomenon that has attracted the attention of astronomers for several decades. Blazars are a class of active galactic nuclei characterized by powerful jets of relativistic particles pointed almost directly at Earth. These jets emit radiation throughout the electromagnetic spectrum, and OJ 287 is particularly notable for its brightness fluctuations, which occur about every 12 years. The periodic activity observed in OJ 287 is explained by the interaction of a supermassive black hole at the center of the galaxy with another black hole. This system consists of a primary black hole actively accreting matter, surrounded by a secondary black hole in a binary system. When a companion black hole orbits around a larger black hole, it exerts a gravitational influence on the material of the accretion disk surrounding the main black hole. This gravitational influence can enhance the accretion process, resulting in increased radiative power as the companion black hole approaches. During periods of increased activity, the energy released as matter spirals into the black hole increases significantly. This outburst leads to a sharp increase in the brightness of the blazar, causing the flares observed from Earth. The mechanism of these flares may also involve a complex interaction of shock waves propagating down the jet, further enhancing the brightness through the Doppler effect as the material travels at close to the speed of light. The cyclicity of OJ 287 strengthens the understanding of black hole interactions in active galactic nuclei. Observations of its amplification not only provide insight into the behavior of matter under extreme conditions, but also help improve our knowledge of the dynamics of such massive systems. OJ 287 serves as a critical source of information in the quest to comprehend the workings of the universe at its most energetic and fundamental levels. Binary systems often go through a stage known as common envelope evolution, which can significantly change their structure. This occurs when one of the stars in a binary expands into a giant star, enveloping the other star in a shared outer layer of gas. Gravitational interactions between two stars can cause an abrupt transformation of their orbits and potentially lead to the ejection of the outer shell. However, some binary systems manage to survive the common shell phase, and this resilience can be explained by several key factors. One important factor is the ratio between the masses of the two stars. If the secondary star is massive enough, it can help stabilize the common envelope phase by retaining some of the material ejected from the primary star. Eventually, this containment may allow the two stars to continue interacting, facilitating additional mass transfer and allowing them to remain bound together. The interaction with the secondary star also helps dissipate energy, which can prevent the envelope from dissipating too much, allowing the binary system to evolve successfully. In addition, the dynamics of the common envelope itself plays a significant role in the outcome. During this phase, stars can undergo dramatic changes, including a rapid decrease in orbital distance. If the energy released when the primary star's envelope collapses into the companion core is enough to completely expel the common envelope, the evolutionary path may lead to a closer binary configuration. A closer orbit could bring the two stars closer together, increasing the rate at which they interact and setting the stage for future evolution. The presence of additional factors, such as the spin and rotation of the stars, can also affect the ability of a binary system to undergo common envelope evolution. The orientation of the star's spins and their magnetic fields can affect the physics of the shell dynamics, thereby influencing whether or not the binary system can survive. In cases where the stars are favorably located, this interaction can help the system maintain its integrity and prevent it from completely collapsing. These mechanisms demonstrate that binary systems are capable of a variety of evolutionary pathways that allow them to adapt and survive even after intense transformations. Understanding how these systems cope with such transitions provides insight into the complex life cycles of stars and the intricate relationships that can form in the cosmos. Each binary system offers a unique story about stellar evolution and the diverse outcomes that can result from the interaction of massive objects in space.
Our view of the stars is limited. What we see in the vastness of the universe is not the big picture, but only a section determined by several natural factors. But what is hidden in the part of the universe that we cannot see? Is there a way to solve this mystery? Well, there is, and the growing evidence suggests that there's something bigger out there that's reaching out into our world. And the Earth is the center of the universe. But before we think we've lost our minds to the Middle Ages, let's briefly explain what this means. The geocentric view of the world, which places everyone at the center of space, has long been obsolete. Nevertheless, our blue home planet is still the center of the observable universe. Because, as mentioned at the beginning, our view of deep space is glowing. The universe is isotropic, that is, a background that always looks the same to an observer, regardless of the observer's orientation. The radius of the observable universe is in turn determined by how far light has traveled to us since the Big Bang. According to the standard cosmological model, the universe was born about 13.8 billion years ago, and the optical barrier can be assumed to be 13.8 billion light-years from us. But this is not true. At this point, we must remember that the universe is constantly expanding, and as a result, the distances it travels are constantly expanding. In simple terms, this means that the viewing horizon is 46 instead of 13.8. 3 billion light-years. The most distant objects we can observe today are 40 million light-years from Earth. As a result, the study of these boundary structures is always optically backward. Since the light emitted from it cannot reach us now, it is impossible to know about the current processes at this distance. Against this background, the question of what exists outside the observable universe is doomed from the start. However, despite all the observational horizons and natural barriers to vision, there are some experts who have cracked this puzzle. As a result, a few years ago, researchers realized a strange phenomenon that contradicts our current assumptions and leads us directly into the deepest secrets of the invisible space. Is there a space giant hiding there? Basically, according to the general assumptions of cosmology, the proper motions of galaxy clusters with respect to the background radiation should be randomly distributed in all directions. And again, for a brief classification, the background rays, or more precisely, the cosmic microwave background rays, represent a relic of the immediate aftermath of the Big Bang that still fills the universe today. Between 2001 and 2010, NASA's Wilkinson Microwave Anisotropic Probe, or WMAP for short, was again dedicated to investigating disturbances in the cosmic background radiation. And the NASA Task Force, in 2008, led by Alexander Kashlinsky, while analyzing the WMAP data, they noticed a strange pattern that shouldn't be there. Scientists did not detect the movement of galaxy clusters scattered in all directions, but a surprisingly uniform flow. This is not the case. In all cases, the galactic flow rate increased with increasing size. The bottom line is that such a phenomenon can only occur due to extreme gravity.
But what structure might be responsible? Well, unfortunately, this question is not entirely reliable. All studied galaxy clusters are moving towards a point outside the observable universe. Henceforth known as the dark stream, the galaxy caravan was re-examined in 2010, which increased the number of galaxy clusters floating in the dark stream from 700 to 1,400. Although there were some differences in the direction of movement in the 4 observed segments, all areas showed a clear correspondence. Since then, astronomers have gathered further evidence of extreme gravity and tantalizing mystery beyond the observable universe. According to Alexander Kashlinsky, for some time the matter in the observable universe cannot explain the measured galactic flow. We don't know in the same breath what is responsible for it. In this regard, a NASA astronomer from the Goddard Space Flight Center is quoted as saying that the dark stream theory has been criticized. So our cosmic field of view hides an accumulation of energy and matter exceeding certain orders of magnitude? Or we do. G here with strange periodic distortion effects from neighboring universes? Critics of the dark current theory are critical of these questions, and for the simple reason that the leading researchers have raised eyebrows. G errors. In this sense, the previous study concluded that it is not a physical flow, because the basic anisotropy, or in other words, the directional dependence of the cosmic background radiation, was neglected in the previous study. Furthermore, the study of more than 550 supernovae also did not reveal an impossible pattern of synchronous motion, but rather a pattern that fits easily into our cosmological models. Then there's the data from ESA's Planck satellite, which has yet to provide any further evidence of a mysterious black stream. So, can we finally save the hidden superstructure theory? Kashlinsky emphasized that the observations were based on data from more than 1,000 billion galaxy clusters that were measured up to 3 billion light-years away. Statistical coincidence can therefore be ruled out, and it is clear that dark currents have not yet been definitively confirmed. The question is, what is behind it? And whatever this may be, if there really is a dark stream generator, it also means that there must be something behind our observable universe. And of course, Kashlinsky's researchers are not the first, nor the only ones, to deal with the question of what might be behind this horror. Needless to say, at this point, dealing with this topic is always pure speculation, but the relevant theories are surprisingly varied. And even if this first hypothesis sounds a bit strange at first, he says, in effect, that the invisible universe is structured in the same way as the observable universe. However, if we move this scenario to infinite space, things get even more fascinating, because eventually we will find different things. And by that, we really mean different things. In this context, there is another solar system, complete with Earth, that is similar to ours in every way, except this one. Maybe you had cornflakes instead of toast this morning. In another solar system, you skipped breakfast altogether. In another, you got up this morning to rob a bank. Some experts even believe that there is an observable universe that is exactly like ours. In other words, there is a version of you in infinite space that accurately reflects everything you do. At first glance, this thought may seem beyond the limits of our imaginations, but infinity also offers endless possibilities. Alternatively, we could be on one of an infinite number of space shuttles. According to Kashlinsky's alternative universe theory, most of the universe is expanding in a perpetual inflationary fashion, a process that stops at most formless subcontinents. Individual sub-universes may contain their own natural fixed values and then individual physical laws. Multivariate theory follows a similar line. According to the motto, there is a whole world that can be imagined. We only exist because the laws of physics are so perfected that there must be a world among countless universes where life can flourish. In detail, the ideas of string theory are now applied to membranes. Broken, the whole point of the whole thing is that these membranes, in the 11th dimension, embody completely different universes. And when they collide, they create a new universe. One of the strangest aspects of this theory is the idea that all the gravity we experience in our universe enters our world in a different dimension from another universe. Ultimately, however, this theory may explain why gravity is so weak compared to the other fundamental forces of physics. If you want the next video to appear on your homepage, you can now concentrate your efforts and hit the subscribe button. Be part of our community and never miss an exciting video from us. See you soon. We humans crave knowledge. The ability to understand the structure and function of our environment has helped our species reach a highly evolved point in its history. Although humanity regularly produces new technological breakthroughs, there are countless realities that almost completely elude our knowledge. Although these mysteries of life raise great question marks among experts on the one hand, the fascination generated by these unsolved mysteries is equally undeniable. This topic becomes especially exciting when it seems beyond our horizons. In the case of the universe, despite all the rockets launched into orbit and the successful moon landing in 1969, research is still in its infancy. At present, we know only a small part of what is hidden from our view in the infinite space. Space. Just how big the universe is in general is a mystery that has plagued humanity for countless centuries. In today's installment, we present the current state of research on this topic. We will show you the current state of astronomical knowledge and discuss why the question of the size of the universe is so difficult to find. If you like our videos, please support us with a thumbs up, subscribe to Simple Space, and look forward to future videos. Let's begin our journey through the vastness of the universe, what we can see about the universe. When we look up at the night sky full of amazing stars, most of us realize that we are small in relation to the big picture. The thousands of twinkling stars in the firmament silently bear witness to the fact that our tiny home planet is only a small part of what we call the universe. However, a quick glance at the sky is enough to realize that the universe must be bigger than we imagine. But can we scientifically understand the magnitude of the universe in detail? This question has always been a central point in the field of cosmological research. Even this question can never be satisfactorily answered. However, this does not necessarily mean that experts will not try to answer it. We now know that the universe was created about 13.8 billion years ago. The process known as the Big Bang describes the formation of matter, space, and time, and is therefore considered the birth of our universe. In physical cosmology, the cosmic microwave background rays play a key role in studying the earliest state of the universe. It is a type of radiation in the microwave range that was created during the Big Bang and flows through the vastness of the galaxy today. By looking at said radiation and measuring it at different distances, researchers were able to determine the approximate age of our universe. At the same time, this also means that we can now look at 13. Space is 8 billion light-years from Earth. If one wants to visualize this situation, one can draw a spherical image with the Earth as the center. The remaining spheres now represent the sphere we can see from our blue home planet. In technical terms, the universe visible to us is called the event horizon. In detail, the event horizon describes the spectrum of objects whose reflected light is visible only from Earth. However, the processes behind this event horizon are currently completely invisible to our human eyes. We don't know exactly what lies behind the observable universe, so the question of the total size of the universe is more difficult to answer. The expansion of the universe. If one accepts the question of the completeness of the universe, an important fact cannot be overlooked. As scientists know today, the universe is always expanding. One object was still around 13 at the time of the Big Bang. 8 billion light-years from Earth, the distance between the celestial body and our planet is now 46 billion light-years due to the expansion of space. This situation also means that in the future, we may see things in the firm that are still hidden from our eyes. At the same time, due to the expansion of the universe, some celestial bodies will disappear from our star charts in the future. Naturally, during these observations, we put the Earth at the center. This is due to spatial conditions, since there is no other way than to define our planet as the central vantage point in the star chart. But at what geographic point our blue home planet is located within the ever-expanding universe is impossible to answer today. Measuring the universe. As we mentioned earlier, an international team of experts is trying to explore all the dimensions of space despite all the difficulties. To do this, experts use several different methods that help researchers study the vast dimensions of the universe. Key research methods include some measurements of early cosmic radiation. Using these radiation movements, scientists can determine different distances and try to calculate the dimensions of the universe. The oldest light source that researchers have been able to detect is 92 billion light-years from Earth. Conversely, however, this does not mean that the object located is an external component of the universe. The question of whether the universe ends is much more difficult to answer than most of us think. Basically, the farther an object is from our planet, the longer it takes for the light it reflects to reach us. Some objects in galaxies are so far away that the light they emit sometimes takes billions of years before we see them from Earth. Therefore, there are countless rays of light in the universe right now that have been traveling through the universe for billions of years, but have yet to reach us. The question of the shape of the universe. To calculate the size of an object, it is necessary to know the corresponding shape of the object. The shape of our universe is still an unsolved question in research that has not been satisfactorily answered. Although some scientists suspect that our universe is built like a self-contained sphere, which may contain other media, other experts believe that the universe is a flat space that is also infinite. If the first thesis were followed, our universe would be a finite self-organizing structure somewhere. So, if our galaxy is indeed a finite construct, at least theoretically, it would be possible for scientists to mathematically determine the dimensions of the universe if they had the right information. However, if our universe is infinite, then the question of size cannot be answered. By definition, infinite objects cannot be assigned any size because they have no mathematically interpretable boundaries. According to NASA, the universe is an infinitely large, flat structure. However, our universe has an infinite age and, as mentioned earlier, was created about 13.8 billion years ago. So we can check the time interval between the Big Bang and today. Unanswered question? Although the international team of experts does not currently know how big the universe is, researchers can say with confidence that the universe is an incredibly large, even infinite structure that exceeds the dimensions of our horizons. The precise study of the universe is a work that will engage countless generations of experts. Although we may never know the vast details of the universe in our lifetimes, this will not diminish our interest in the fascinating world of alien stars and planets. What do you think about the true size of the universe? Do you think the universe is a closed entity or an infinite structure? Feel free to let us know your thoughts on this topic in the comments. Thank you very much, and see you next time. If you follow our channel or astronomy developments regularly, you probably know that the new James Webb Space Telescope is completely revolutionizing the way we look at the universe. Last September, NASA released another image of the new super telescope, quite a lot of noise. The image shows the icy planet Neptune. and it's the best we've seen of this fascinating planet in 30 years. In fact, Neptune is one of the least studied and most mysterious planets in the solar system. Before moving on to the blue ice giant, we invite you to subscribe to our channel if you haven't already done so, and activate the notification bell so you are guaranteed not to miss any of us. Future videos. Also, if you enjoyed the latest discoveries about Neptune, give us a like at the end of the video. Now we start with a few facts about the blue planet at the end of the solar system. Neptune facts. Neptune is the 8th known planet in the solar system, and since Pluto was stripped of planet status in 2006, the latter is measured by diameter, making Neptune the 4th largest, 3rd most massive and densest planet. In the solar system, it has about 17 times the mass of Earth and is slightly more massive than its identical twin, Uranus. Neptune is composed mainly of gases, liquids, and ice. Officially, it's an ice giant. One orbit around the Sun requires Neptune to be at a distance of 8 billion miles, 164.8 Earth years. Neptune was the first planet discovered using only mathematical calculations. Galileo Galilei saw a blue sky in the 17th century, but he mistook Neptune for a star. It wasn't until 1846 that British mathematician and astronomer John Couch Adams discovered through mathematical calculations that there must be another planet behind Uranus. Discovered in 1781, Couch's calculations were confirmed simultaneously by the French astronomer Urbain Le Verrier. The planet was first seen on September 23, 1846, by a German astronomer named Johann Gottfried Halle. Looking at the night sky from the Berlin Observatory, he named Neptune the 8th planet in the solar system. Trademark of Neptune its blue color. This is due to the peculiar vibrational pattern of the molecular structure in methane gas, which makes up the bulk of Neptune's structure. The blue color also gave the planet its name as the god of the sea. Neptune is one of the least studied planets to date. Observations of the planet's atmosphere over the past few decades have shown sometimes dramatic changes in the ice giant's structure. This caused great concern among scientists. Because so little is known about Neptune, researchers don't know what to do with these observations. Image of Neptune by James Webb. The first exciting images of Neptune were provided by the Voyager spacecraft in 1989. A probe launched in 1977 reached the planet after a 12-year flight. Neptune, however, was not Voyager's target. Voyager's binary probe is designed to fly through the entire solar system and then enter interstellar space. This image was to remain the best for humanity on Neptune for over 30 years. The first Hubble Space Telescope also provided images of the ice giant, but the quality was mediocre. Scientists are even more excited about the launch of the new James Webb Telescope. In September 2022, we saw Neptune in a completely new light. Webb not only captured the clearest view of this distant planet's rings in more than 30 years, but his cameras also show the ice giant in a whole new light. Image captured by NIRCam, infrared camera, in the infrared range of 0.6 to 5 microns. In this way, Neptune does not appear blue, but is very dark. The dark spots are probably methane gas that absorbs red and infrared light. Bright lines and spots, on the other hand, methane ice clouds. They are almost white due to the reflection of sunlight. With this technique, Neptune's fine ring system was clearly visible for the first time. These rings have been known to scientists for a long time, but prior technology could not visualize or image the rings. Made of ice crystals, a thin, bright line circling the planet's equator indicates atmospheric circulation. Simply put, these are the strong winds and storms on Neptune's surface. A previously known vortex at the South Pole is clearly visible in James Webb's image. Also, the first is a depiction of a continuous cloud band covering the planet at high latitudes. Light filtering techniques allow scientists on Earth to determine the precise composition of gases and other structures. Study the rings alone. First observed by Voyager 2 in 1989, it will provide exciting new information about the ice giant at the end of the solar system. For astronomers, this is a milestone in the study of Neptune, and a long-awaited relief for NASA's current lack of funding for its own Neptune exploration. Big Dark Spot, Neptune's surface processes, are among the last great mysteries of the star system. In 1989, Voyager 2 discovered the Great Black Spot during a flyby of Neptune's southern hemisphere. It is a giant storm similar to Jupiter's Great Red Spot. In 1994, using the Hubble Space Telescope, a team of researchers took a closer look at the Great Dark Spot. The researcher was surprised that a high-pressure area the size of Eurasia suddenly disappeared. Instead, scientists discovered a new dark spot in the northern hemisphere. Its disappearance a few years later suggests that the large storms that dominate Neptune's surface are shorter-lived than Jupiter's. On its surface, a storm called the Great Red Spot has persisted for centuries and in the same place. Neptune's storms may be shorter than those of its older brother Jupiter, but when it comes to wind speeds, Neptune is the undisputed king in the system. Its gusts reach 1,305 miles per hour. In comparison, the strongest tropical cyclone reaches 186 miles per hour. So you really don't want to face a Neptune storm. Mysterious processes on Neptune's surface. In 2020, scientists are thrown into chaos. A team of researchers from the University of California, Berkeley, using the Hubble Space Telescope, observed a storm that was wider than the Atlantic Ocean. The storm originated in the northern hemisphere of the planet. Since its opening in 2018, Berkeley experts have looked at what's going on every year. In 2019, the storm began to turn south. Moving toward Neptune's equator is where storms typically occur. But to scientists' surprise, Hubble found that in August 2020, the vortex had changed direction and was heading north. Although Hubble had been observing similar black spots for nearly 30 years, this atmospheric behavior was completely new. Researchers don't know what these movements mean, or whether the events are rare or worrisome anomalies. The largest hurricane ever seen at Neptune was 4,600 miles in diameter. Researchers have been tracking the storm's behavior since 1993, and they have seen the storm disappear several times, perhaps dissipating and appearing not far from where it disappeared. Scientists would like to know more about these events. The theory says that the storms only disappear from the surface, but continue to rage in the deep layers of Neptune. From time to time, events could be seen again on Earth. We still don't know what happens in the deep layers of Neptune. NASA was supposed to send a probe to the blue planet. Like Cassini, it can be brought down to the planet after its mission is over. During a flyby through Neptune's layers, researchers could finally get at information they missed. It's still a pie-in-the-sky idea, but there's no doubt that Neptune will get its own investigation at some point. Perhaps NASA will combine a mission to Neptune with a search for the mysterious Planet X, whose orbit is said to be behind Neptune. Since Pluto is no longer a planet, Neptune is the eighth and last of the main planets in the system. However, orbital calculations of some objects in the solar system indicate that there must be another large planet behind Neptune. Planet 9, or Planet X, orbits the Sun in a very eccentric orbit that is not even visible due to poor light conditions. If Planet X is in orbit, its orbital period around the Sun could be as long as 1,000 years. Theoretically, this planet will be visible with modern telescopes every few hundred years. Neptune's largest moon, Triton. We conclude with another look at James Webb's new image. Surely, when you saw the photo, you immediately wondered what the blue-green fire in the background of Neptune is. Well, even though this scene looks like a bright shining star, the mysterious green glow is just the moon. This image shows 7 of the 14 Neptune moons known so far, and the one that shines so brightly is Triton. Triton is the largest of Neptune's moons and the size of Earth's moon. Because it orbits the moon in a highly elliptical orbit, researchers speculate that Triton may have once been a Kuiper belt object that was pulled by Neptune's gravity. The moon appears green in this image due to special filtering of the image. As an icy moon, Triton also rarely reflects sunlight well. Triton, Jupiter's moon Europa, and Saturn's moon Enceladus have similar ice volcanism. There may even be a liquid ocean beneath the moon's icy crust. So the Neptune zone would have a lot to learn about this part of the solar system. Until then, we're curious to see what new observations the James Webb Telescope will surprise us with. Apparently, researchers are now looking at Neptune regularly with the new telescope. If there are new interesting discoveries, you will definitely know here. Finally, leave us a comment and think about the latest discoveries around Neptune and the interesting image from the James Webb Telescope. We'd love for you to join us today and watch. Next time in Plain Space,